Right now, as you listen to this, something absolutely enormous is lurking at the heart of our galaxy. It's invisible, it's incredibly powerful, and it's holding together hundreds of billions of stars in a cosmic dance that's been going on for billions of years. We're talking about Sagittarius A, the supermassive black hole at the very center of the Milky Way. This isn't just any black hole. This is our galaxy's dark heart, a monster that weighs roughly 4.3 million times what our Sun weighs, all packed into a space that would fit comfortably inside Mercury's orbit. For decades, scientists suspected it was there. They could see stars whipping around something invisible at ridiculous speeds. They could detect strange radiation coming from the galactic center. But they couldn't see it directly. How do you photograph something that doesn't let light escape? Then, in 2022, we finally got our first image of it. And what we learned from that image, combined with decades of observations, has revealed secrets about our galaxy that change how we understand everything from how galaxies form to the very nature of space and time itself. In the next 2 hours, I'm going to take you on a journey to the center of our galaxy. We're going to explore what this black hole really is, how it got there, what it's doing right now, and what its existence tells us about the universe we live in. We're going to meet the stars that orbit so close to it that they complete an entire orbit in just years, traveling at a decent chunk of the speed of light. We're going to talk about the weird physics that happens when gravity gets this extreme. And we're going to explore the biggest mysteries that still surround this cosmic giant. Before we start, if you enjoy these kinds of explorations, a quick like or subscribe would help keep this channel going. It's a small thing, but it means a lot. Now, settle in. We're about to take a trip to the most extreme environment in our entire neighborhood of space. We're heading to the dark heart of the Milky Way. Let's start with the basics. What exactly are we dealing with here? At the center of our galaxy sits what astronomers call a supermassive black hole. Now, black holes come in different sizes. You've got stellar mass black holes, which form when massive stars die. Those typically weigh anywhere from a few times to a few dozen times the mass of our Sun. Then you've got intermediate mass black holes, which are rarer and weigh hundreds or thousands of solar masses. And then you've got the big ones, the supermassive black holes. These monsters weigh millions or even billions of times what our Sun weighs. And here's the weird thing. We find them at the centers of most large galaxies. Not some galaxies, most galaxies. It's like galaxies and supermassive black holes go together like peanut butter and jelly. Our galactic center monster, which scientists often call SGR, or just SAG-R, sits right at the gravitational center of the Milky Way. It's located in the direction of the constellation Sagittarius, hence the name. The mass is extraordinary. Our Sun already makes up 99.8% of all the mass in our entire solar system. Everything else, all the planets, moons, asteroids, comets, and dust combined, is just 0.2%. Now, multiply that solar mass by over 4 million. That's the scale we're dealing with. But here's where it gets even stranger. Despite having all that mass, the actual event horizon, the point of no return, has a diameter of only about 24 million kilometers. That's compact enough to sit well within the orbit of Mercury, our solar system's innermost planet. That's the nature of black holes. They pack enormous amounts of mass into incredibly small spaces. The density is off the charts. Think about it this way. If you could somehow weigh a teaspoon of material from near the event horizon, assuming you could even extract it, that teaspoon would weigh more than Mount Everest. The compression of matter reaches levels that make our everyday intuitions completely useless. Now, you might be wondering how we know all this if we can't see the black hole directly. That's a great question, and it gets to the heart of how science actually works. For most of human history, we didn't know there was anything special at the center of the Milky Way. We couldn't see the galactic center at all in visible light because there's too much dust and gas in the way. It's like trying to see through fog. But in the 1930s, Carl Jansky at Bell Labs detected radio waves coming from space. He was trying to figure out what was causing static in radio communications, and he discovered some was coming from the direction of Sagittarius. He'd accidentally discovered radio astronomy. Over the following decades, as radio telescopes improved, astronomers mapped the galactic center in more detail. By the 1970s, they'd identified a particularly bright radio source right at what appeared to be the very center. That's what they called Sagittarius A. But they didn't know it was a black hole yet. They knew something weird was there, something producing a lot of energy, but they couldn't say for sure what it was. The real breakthrough came from studying the stars around it. In the 1990s, two teams of astronomers, one led by Andrea Ghez at UCLA and another led by Reinhard Genzel at the Max Planck Institute, started using advanced telescopes to track individual stars very close to the galactic center. This was incredibly difficult work. They developed techniques using infrared light, which penetrates dust better than visible light, and adaptive optics technology that compensates for atmospheric blurring in real time. What they saw was absolutely remarkable. Stars were orbiting something invisible at incredible speeds. Some were moving at more than 5,000 kilometers per second. That's almost 2% of the speed of light. The star they watched most carefully is called S2. This star orbits every 16 years in a highly elliptical path. At its closest approach, S2 comes within about 17 light hours of the black hole and reaches speeds of roughly 7,600 kilometers per second. But S2 isn't even the closest. By 2025, astronomers had identified even more extreme objects. Stars like S29 and especially the S4714 family get closer and move faster. S4714, discovered through careful observations over the last few years, zips around the black hole at speeds approaching 8% of the speed of light. That's 24,000 kilometers per second. At those speeds, relativistic effects become impossible to ignore. Time dilation, length contraction, all of that weird stuff from special relativity starts to matter significantly. By carefully tracking these stars over many years, the teams could calculate exactly how much mass was contained in the region they were orbiting. The answer was clear. There was roughly 4.3 million solar masses in a region of space too small and too dark to be anything but a supermassive black hole. This work was so important that Andrea Ghez and Reinhard Genzel shared the Nobel Prize in Physics in 2020 for it. They'd proven that the Milky Way has a supermassive black hole at its center, and they'd measured its properties with incredible precision. But even then, we still hadn't actually imaged the black hole itself. We'd imaged the stars around it. We'd detected radio emissions from materials swirling around it. But we hadn't captured a direct image of the shadow of the black hole against the light behind it. That changed in 2022. In May of 2022, the Event Horizon Telescope collaboration released the first ever image of Sagittarius A, and it was profound. The Event Horizon Telescope isn't a single telescope. It's a network of radio telescopes scattered around the planet, from Hawaii to the South Pole, working together using a technique called very long baseline interferometry. By combining observations from telescopes spread across Earth, they effectively created a telescope the size of the planet itself. Even with that, imaging our galactic center was incredibly difficult. The black hole is tiny on the sky, like trying to see a donut on the moon from New York. And unlike the M87 black hole they'd imaged earlier, Sagittarius A changes quickly. The material around it swirls in just minutes to hours. like trying to photograph a squirming toddler with a long exposure. But they did it. The image shows exactly what Einstein's general theory of relativity predicts. There's a dark region in the center, the shadow of the black hole, surrounded by a bright ring of light from superhot material orbiting at close to light speed. The ring isn't perfectly uniform. There are brighter and dimmer spots telling us about magnetic fields in the region and how material flows into the black hole. What's really significant is that the image matches theoretical predictions perfectly. The size of the shadow, the brightness of the ring, the way light is distributed, all of it fits with our understanding of how gravity works in extreme conditions. Since that first image, the team has continued analyzing their data. In 2024 and 2025, they released results from polarized light observations, which reveal the structure of magnetic fields threading through the accretion disk. These magnetic fields appear to be incredibly strong and well organized, suggesting they play a major role in how material spirals inward. The polarization data also provided better constraints on the black hole's spin. The latest analyses suggest it's spinning rapidly, with a spin parameter above 0.9. That means the event horizon is rotating at more than 90% of the maximum rate allowed by physics. At that speed, the black hole drags space and time around with it, creating extreme frame dragging effects that influence everything nearby. Understanding the spin is crucial because it tells us about the black hole's history. A rapidly spinning black hole probably grew through smooth, organized accretion of gas, all rotating in the same direction. A slowly spinning, one might have grown chaotically through random mergers and gas clouds falling in from different directions. Our black hole's high spin suggests a relatively orderly feeding history over billions of years. Now that we've established what's at the center of our galaxy, let's talk about something that makes this black hole particularly fascinating compared to others in the universe. Sagittarius A is what astronomers call a remarkably quiet, supermassive black hole. Most black holes, this massive that we can observe, are feeding voraciously, shining brightly as they tear apart stars and consume vast quantities of gas. They're called active galactic nuclei, and they can outshine entire galaxies. Our black hole isn't like that. It's dormant, barely sipping on the thin gas that drifts nearby. Astronomers estimate it's only consuming material equivalent to feeding it an asteroid every few centuries. For something with over 4 million solar masses, that's practically nothing. This quietness is actually a mystery. The galactic center isn't lacking in material. There's gas floating around, stars passing by. So why isn't the black hole feeding more aggressively? One possibility is that the gas near the black hole is just too hot. When gas is extremely hot, it has a lot of random motion. This means it has too much energy to easily fall inward. Instead of spiraling smoothly into the black hole, hot gas can actually be blown away by radiation pressure before it gets close enough to be captured. Another factor might be magnetic fields. The region around the black hole is threaded with powerful magnetic fields that can actually prevent gas from falling in smoothly. These fields can channel gas into specific patterns, sometimes even flinging it away rather than letting it accrete. But the black hole's quietness is deceptive. Even in its dormant state, weird things are happening very close to the event horizon. X-ray telescopes have detected brief flares, sudden brightening events that last minutes to hours. These flares happen when small clumps of gas, or maybe even asteroids, fall into the accretion disk and heat up dramatically before disappearing. Some of these flares are extraordinarily bright, briefly outshining everything else at the galactic center. They're like the black hole hiccuping brief moments of activity in an otherwise sleepy giant. One particularly interesting phenomenon is what scientists call quasi-periodic oscillations. These are patterns in the brightness that repeat on roughly regular timescales. They might be caused by hot spots in the accretion disk orbiting the black hole, or by instabilities in the magnetic field structure. Understanding these oscillations helps astronomers figure out exactly what's happening in that chaotic region right at the edge of the event horizon. There's also evidence that the black hole might have a jet, though it's incredibly weak compared to jets from active black holes. Some radio observations suggest there's a faint outflow of material moving away from the black hole at high speed. If confirmed, this would tell us something important about how even quiet black holes can still influence their surroundings. The material swirling around the black hole exists in one of the most extreme environments imaginable. This accretion disk isn't like the smooth, orderly disks you might picture around young stars. It's chaotic, turbulent, and violently energetic. Gas in the accretion disk is moving at significant fractions of the speed of light. As it orbits, friction between layers moving at different speeds generates tremendous heat. We're talking temperatures in the millions of degrees. At those temperatures, atoms are completely stripped of their electrons, creating a plasma that glows across multiple wavelengths. But what's really interesting is how the disk is structured. It's not a simple flat disk. Recent observations suggest it has a complex three-dimensional structure with material flowing in at different angles and heights above the equatorial plane. The magnetic fields threading through the disk play a crucial role. These fields aren't just passive traces of gas motion, they actively shape how material flows. Magnetic field lines can become twisted and tangled by the disk's differential rotation, building up tension until they snap and reconnect, releasing enormous amounts of energy in the process. This magnetic reconnection might be what causes those sudden X-ray flares we detect. When field lines snap and reconnect, they can heat small regions of the disk to incredibly high temperatures, causing them to briefly outshine everything else. The disk also interacts with the black hole's spin in fascinating ways. A rapidly spinning black hole drags space-time around with it through frame dragging. This means the inner edge of the accretion disk doesn't orbit in a fixed plane. Instead, the plane of the disk precesses, wobbling like a spinning top that's starting to tip over. This precession happens on timescales of minutes to hours for the innermost material. Astronomers think this might explain some of the variability we see in the emission from the galactic center. As the disk wobbles, different parts of it come into and out of our line of sight, changing what we observe. There's also the question of where the material in the disk comes from. Some of it is probably from stellar winds, material blown off by massive stars near the galactic center. Some might be from gas clouds that wandered too close. And occasionally, a star might get disrupted by tidal forces, adding a sudden influx of material. One mystery is why so little of this material actually makes it all the way to the event horizon. Most of the gas seems to be blown away before it can fall in. Observations suggest that winds and outflows carry away 99% or more of the material that reaches the inner accretion disk. Only a tiny fraction actually crosses the event horizon. This inefficiency is part of why our black hole is so quiet. If even 10% of the nearby gas was falling in, the galactic center would be dramatically brighter than it is. The population of stars orbiting very close to the black hole is one of the most fascinating aspects of the galactic center. These aren't normal stars in normal orbits. These are stars living on the edge, literally. Beyond the well-studied S2 star we discussed earlier, astronomers have now catalogued dozens of stars in tight orbits, and the discoveries keep coming. The observations have revealed a strange and unexpected population. First, there's the mystery of the young, massive stars. Within a few light years of the black hole, there's a cluster of stars that are extraordinarily massive and surprisingly young. These are O-type and Wolf-Rayet stars, some weighing more than 100 times the Sun's mass, and they're only a few million years old. This is deeply puzzling. The tidal forces near a supermassive black hole should prevent star formation. Any gas cloud trying to collapse into a star should be ripped apart before it can finish forming. So how did these massive stars get there? One theory is that they formed in a massive gaseous disk that existed around the black hole several million years ago. This disk would have been dense enough and massive enough that stars could form within it, despite the tidal forces. After the stars formed, the disk was dispersed, leaving the stars behind in their current orbits. Another theory suggests these stars formed farther out and migrated inward through gravitational interactions with other stars and possibly with an intermediate mass black hole that may once have orbited in the region before being consumed by the central black hole. We still don't know for sure, but the presence of these young stars tells us the galactic center has a dynamic history we're only beginning to understand. Then there are the G objects. These are strange, dusty sources that look like gas clouds but behave like stars. G1 and G2 were discovered over a decade ago, and by 2025, astronomers had identified at least 6 of these objects, labeled G1 through G6. G2 made headlines in 2014 when it was predicted to pass very close to the black hole. Many expected it would be torn apart spectacularly, feeding the black hole and causing a bright flare. But G2 survived the encounter largely intact, stretched out but not destroyed. The leading explanation now is that the G objects aren't simple gas clouds. They're probably stars, possibly binary star systems, that are surrounded by thick shells of dust and gas. The dust obscures the stars at some wavelengths, making them look like clouds, but the stars provide enough gravity to hold the material together as it passes the black hole. Understanding these G objects is important because they might tell us about star formation or stellar evolution in extreme environments. There's also growing evidence for more exotic objects orbiting the black hole. Some theories suggest there could be smaller black holes, perhaps stellar mass black holes or even intermediate mass ones, orbiting the supermassive black hole. These would be essentially invisible, detectable only through their gravitational effects on other stars. In fact, some of the orbital peculiarities observed in the S-star population might be explained by gravitational perturbations from unseen companions. It's like looking at a chandelier swaying and inferring that air currents you can't see must be disturbing it. The discovery of these orbiting stars has also opened up a new way to test physics. The orbits themselves are laboratories. When S2 passes close to the black hole, its orbit should precess, meaning the ellipse should slowly rotate over time. This precession is predicted by general relativity, and observations have confirmed it's happening exactly as Einstein's equations predict. But future observations might reveal deviations. If general relativity isn't quite right, if there are modifications needed to account for quantum effects or dark matter, the orbits of these stars might be the first place we see evidence of it. Tidal forces are the difference in gravitational pull across an object. For most situations, they're negligible. But near a black hole, they become extreme and deadly. If a star gets close enough, the gravitational pull on its near side becomes so much stronger than the pull on its far side that the star literally gets stretched apart. The star becomes a long stream of gas, like pulling taffy. Half of that gas typically has enough energy to escape, flung away at high speed. The other half falls into the accretion disk and eventually into the black hole. The process releases a tremendous amount of energy, causing the black hole to flare in brightness for weeks or months. We've observed tidal disruption events around other supermassive black holes in other galaxies. They're rare, maybe happening once every 10,000 to 100,000 years per galaxy. When they do happen, they're spectacular, sometimes outshining the entire host galaxy. We haven't seen one happen at our galactic center in recorded history. But that doesn't mean they don't occur. We just haven't been watching with the right instruments at the right time. The question is, when will we see the next one? There are stars in very close orbits that will eventually spiral inward. Some of the G objects might be on trajectories that could lead to disruption. And there are likely many stars we haven't discovered yet on orbits that might bring them close enough. When it happens, it will be incredible to watch. We'll see the star stretched into a stream. We'll observe as one end falls toward the black hole while the other escapes. We'll detect the X-ray flare as the material heats up in the accretion disk. And we'll be able to study the event with instruments far more sophisticated than anything previous generations had. It might happen tomorrow. It might not happen for 10,000 years, but the stars are there, orbiting, gradually spiraling inward. Eventually, one will get too close. One of the most important properties of the black hole is its spin. And thanks to recent observations, particularly from the Event Horizon Telescope's polarization measurements in 2024 and 2025, we now have much better constraints on this. The latest data suggests the black hole is spinning rapidly, with a spin parameter above 0.9. That's more than 90% of the maximum rate allowed by physics. This is significant because spin affects everything about how the black hole interacts with its surroundings. A spinning black hole drags space-time around with it in an effect called frame dragging. This creates a region called the ergosphere where nothing can stay still. Everything must rotate in the same direction as the black hole. The ergosphere extends beyond the event horizon. For a rapidly spinning black hole like ours, the ergosphere is substantial, and the frame dragging effects influence the entire inner accretion disk. This spin also affects the innermost stable circular orbit, the closest distance at which matter can orbit without falling in. For a non-spinning black hole, this orbit is at 3 times the radius of the event horizon. For a maximally spinning black hole, it can be as close as half that distance. By studying X-ray emissions from the inner accretion disk, astronomers can estimate where this innermost orbit is, which tells them about spin. The polarized light observations from the Event Horizon Telescope provide another way to measure spin, because the polarization pattern depends on how magnetic fields are dragged around by the black hole's rotation. The high spin tells us something about the black hole's history. It probably grew through steady accretion of gas that was all rotating in roughly the same direction. If it had grown through chaotic mergers or by consuming gas from random directions, its spin would be lower. In theory, you can extract energy from a spinning black hole through processes like the Penrose process. If you drop something into the ergosphere on just the right trajectory, it can split into 2 pieces, with one falling into the black hole and the other escaping with more energy than the original object had. The extra energy comes from the black hole's rotation. This sounds like science fiction, but it's real physics. It might even be happening naturally in the accretion disk, where magnetic field lines threading through the ergosphere could extract rotational energy and channel it into jets. This brings us to one of the biggest mysteries in astrophysics. Where did supermassive black holes come from in the first place? We know stellar mass black holes form from the deaths of massive stars. A star 20 times the mass of the Sun or more goes supernova, and if enough material collapses, it forms a black hole. That process is well understood. But supermassive black holes are millions or billions of times more massive than stellar black holes. You can't make a supermassive black hole just from one star, no matter how massive. So did supermassive black holes grow from smaller ones? Did stellar mass black holes form first, then gradually consume gas and merge with other black holes over billions of years until they became supermassive? That's one theory, but there's a problem. We've found supermassive black holes in the early universe less than 1 billion years after the Big Bang. That's not much time for a stellar mass black hole to grow into a billion solar mass monster. To grow that fast, a black hole would have to be feeding at close to the maximum possible rate, a rate called the Eddington limit, all the time for hundreds of millions of years. And even then, it's not clear you could grow fast enough. So there must be another way to make supermassive black holes. Maybe they started big. One idea is that in the early universe, there were ways to form much larger black holes directly without going through the stellar black hole phase. Maybe there were massive gas clouds that collapsed directly into black holes, weighing thousands or even millions of solar masses right from the start. Those intermediate mass seeds could then grow into supermassive black holes more easily. Another idea involves very massive stars that might have existed only in the early universe. These would be stars weighing hundreds of thousands of solar masses, much bigger than any star we see today. Such stars might collapse directly into massive black holes without exploding as supernovae. We don't know which of these scenarios, if any, is correct. It's possible that different supermassive black holes formed in different ways, and the truth is some combination of all these mechanisms. What about Sagittarius A star specifically? How did it get to be 4 million solar masses? Sagittarius A star is relatively small for a supermassive black hole. The black hole at the center of M87, the first one the Event Horizon Telescope imaged, is 6.5 billion solar masses. That's more than 1,000 times bigger than Sagittarius A star. There seems to be a relationship between the mass of a galaxy's central black hole and the mass of the galaxy itself. More massive galaxies have more massive black holes. The relationship isn't perfect, but it's strong enough that it must be telling us something about how galaxies and black holes grow together. The Milky Way is a large galaxy, but not the largest. It has a few 100 billion stars, so it makes sense that it would have a supermassive black hole on the smaller end of the scale. Sagittarius A star probably grew primarily by accreting gas over billions of years, with occasional contributions from stars that got too close and from mergers with smaller black holes. The Milky Way has undergone mergers with smaller galaxies over its history, and those smaller galaxies might have had their own black holes that eventually merged with Sagittarius A star. In fact, we might be able to see evidence of past mergers by studying the orbits of stars around the black hole and looking for patterns that suggest the system was recently disturbed. Another idea involves very massive stars that might have existed only in the early universe. These would be stars weighing hundreds of thousands of solar masses, much bigger than any star we see today. Such stars might collapse directly into massive black holes without exploding as supernovae. We don't know which of these scenarios, if any, is correct. It's possible that different supermassive black holes formed in different ways, and the truth is some combination of all these mechanisms. What about Sagittarius A star specifically? How did it get to be 4 million solar masses? Sagittarius A star is relatively small for a supermassive black hole. The black hole at the center of M87, the first one the Event Horizon Telescope imaged, is 6.5 billion solar masses. That's more than 1,000 times bigger than Sagittarius A star. There seems to be a relationship between the mass of a galaxy's central black hole and the mass of the galaxy itself. More massive galaxies have more massive black holes. The relationship isn't perfect, but it's strong enough that it must be telling us something about how galaxies and black holes grow together. The Milky Way is a large galaxy, but not the largest. It has a few 100 billion stars, so it makes sense that it would have a supermassive black hole on the smaller end of the scale. Sagittarius A star probably grew primarily by accreting gas over billions of years, with occasional contributions from stars that got too close and from mergers with smaller black holes. The Milky Way has undergone mergers with smaller galaxies over its history, and those smaller galaxies might have had their own black holes that eventually merged with Sagittarius A star. In fact, We might be able to see evidence of past mergers by studying the orbits of stars around the black hole and looking for patterns that suggest the system was recently disturbed. The environment around Sagittarius A star is unlike anywhere else in the galaxy. It's crowded, it's energetic, and it's full of weird phenomena. First, there's just a lot of stuff there. The central few light years of the galaxy contain millions of stars packed into a region that, by galactic standards, is tiny. The density of stars is about 1,000,000 times higher than it is in our neighborhood. If you were on a planet orbiting a star near the galactic center, your night sky would be spectacular. Instead of a few thousand visible stars like we see from Earth, you'd see millions. The sky would be so bright with stars that you'd cast a shadow at night. But it would also be dangerous. With so many stars packed so close together, gravitational interactions would be common. Stellar encounters, where two stars pass close enough to perturb each other's orbits, would happen all the time. That makes it hard for planets to maintain stable orbits. There's also a lot of radiation. The stars in the galactic center include many massive, hot, young stars that pump out intense ultraviolet radiation. And Sagittarius A star itself, even in its current quiet state, produces X-rays and other high-energy radiation from its accretion disk. All that radiation makes it hard for complex molecules to survive. Any organic molecules would be quickly broken apart. This probably isn't a great place to look for life. Then there's the gas. The galactic center has a lot of gas, both in the accretion disk around Sagittarius A star and in larger clouds in the region. One of the most studied features is a cloud called G2. G2 was discovered in 2011, and it was predicted to make a close pass by Sagittarius A star in 2014. Astronomers were excited because they thought it might be a gas cloud that would be disrupted by the black hole's tidal forces, potentially causing a flare in activity as the gas fell in. People watched carefully as G2 approached, and, well, not much happened. The cloud survived more or less intact. It got stretched out a bit, but it didn't fall apart and feed the black hole as dramatically as some had predicted. This led to a revised understanding of what G2 is. It's probably not just a gas cloud. There might be a star or binary system hidden inside the gas, and that star's gravity is holding the cloud together as it orbits the black hole. But G2 is just one of many gas clouds and structures in the region. There are streamers of gas, dusty filaments, and shells of material blown out by stellar winds and past explosions. The whole region is a dynamic, churning environment. There are also massive star clusters near the galactic center. One of the most prominent is the Arches cluster, which contains over 100 massive young stars packed into a region only a light year across. These stars are burning bright and will live fast, die young, probably ending as supernovae or black holes within just a few million years. Another notable feature is a population of magnetars in the region. Magnetars are neutron stars with incredibly strong magnetic fields, the strongest magnetic fields we know of anywhere in the universe. They occasionally produce bursts of X-rays and gamma rays when their crusts crack or when their magnetic fields reorganize. One magnetar near the galactic center, called SGR 1745-2900, produced a giant flare in 2004 that was so intense it affected Earth's upper atmosphere from 26,000 light-years away. The presence of so many extreme objects in one region makes the galactic center a uniquely valuable laboratory for studying physics in extreme conditions. When you look at the galactic center in radio wavelengths, you see a lot more than just Sagittarius A star. You see filaments, arcs, and loops of radio emission threading through the region. One of the most striking features is called the radio arc, This is a set of long, thin filaments of synchrotron radiation stretching for hundreds of light-years perpendicular to the plane of the galaxy. Synchrotron radiation is produced when charged particles, usually electrons, spiral along magnetic field lines at close to the speed of light. The fact that we see these filaments tells us there are strong magnetic fields in the galactic center, and those magnetic fields are filled with high-energy particles. But where do the magnetic fields come from, and where do the high-energy particles come from? Part of the answer probably involves past activity from Sagittarius A star. When the black hole was more active, it might have produced jets or winds that carried energy and magnetic fields out into the surrounding region. Part of the answer might also involve supernova explosions. Massive stars in the galactic center explode as supernovae, and those explosions generate shock waves that accelerate particles to high energies and amplify magnetic fields. And part of the answer might involve processes we don't fully understand yet. The interaction between supernova remnants, stellar winds, magnetic fields, and the ambient gas in the galactic center is complex, and we're still working out all the details. What's clear is that the galactic center is not a quiet place, even if Sagittarius A star itself is currently subdued. Let's zoom out a bit and think about the bigger picture. What role does Sagittarius A star play in the Milky Way as a whole? For a long time, astronomers thought of supermassive black holes as passive objects, just sitting at the centers of galaxies. Products of galactic evolution, but not really influencing anything outside their immediate vicinity. But we now know that's not true. Supermassive black holes can have profound effects on their host galaxies, especially when they're actively feeding. The energy released by matter falling into a supermassive black hole can be enormous. A black hole feeding at the Eddington limit, the maximum sustainable rate, can release energy equivalent to turning about 10% of the infalling mass directly into energy via E equals mc squared. To put that in perspective, nuclear fusion, the process that powers stars, converts about 0.7% of mass into energy. Black hole accretion is more efficient than fusion by more than a factor of 10. Where does all that energy go? Some of it gets radiated away as light and other forms of radiation, but a lot of it goes into heating and blowing away the surrounding gas. This is called feedback. The black hole feeds on gas, releases energy, and that energy pushes the gas away, which limits how much the black hole can feed. It's a self-regulating process. But it also affects star formation. Gas that gets blown away by the black hole can't collapse to form new stars. So active supermassive black holes can actually shut down star formation in their galaxies. This is thought to be a major factor in why the most massive galaxies in the universe are mostly red and dead. They're full of old stars and not making many new ones. The supermassive black holes at their centers got so massive and so active that they blew out most of the gas, quenching star formation. The Milky Way hasn't reached that point. We're still forming stars at a decent rate. But Sagittarius A star has probably influenced our galaxy's evolution over billions of years, especially during periods when it was more active. There's also the fact that the black hole's gravity organizes the central region of the galaxy. The stars near the galactic center are all orbiting Sagittarius A star. Their motions are controlled by its gravitational influence. In a sense, the black hole is the anchor that holds the inner galaxy together. Some simulations suggest that without supermassive black holes, galaxies might not form the same way. The early phases of galaxy formation might involve bursts of star formation and black hole growth that are intimately connected, shaping each other through feedback processes. So even though Sagittarius A star is just 0.000005% of the Milky Way's total mass, a tiny fraction, it plays a role in our galaxy's structure and evolution that's way out of proportion to its mass. What's going to happen to Sagittarius A star in the future? In the short term, not much. The black hole will continue to feed slowly on the gas and occasional stars in its vicinity. It will continue to sit at the gravitational center of the galaxy. And we'll continue to study it with ever-improving telescopes and techniques. But in the long term, things get interesting. The Milky Way is on a collision course with the Andromeda galaxy. Right now, Andromeda is about 2.5 million light-years away and approaching us at about 110 kilometers per second. In about 4.5 billion years, the two galaxies will collide. Now, when we say galaxies collide, we don't mean stars will crash into each other. Space is mostly empty. Even in a galactic collision, the stars will mostly pass by each other like two swarms of bees interpenetrating without individual bees colliding. But the collision will be spectacular nonetheless. The gravitational interactions will fling stars into new orbits, trigger bursts of star formation as gas clouds collide and compress, and generally reorganize both galaxies completely. And at the centers of both galaxies are supermassive black holes. Andromeda has one too, somewhat larger than Sagittarius A star, weighing in at around 100 to 200 million solar masses. When the galaxies merge, those two black holes will eventually sink to the center of the merged system. They'll orbit each other, gradually spiraling closer due to gravitational wave radiation, and eventually they'll merge into a single, larger black hole. That merger will be an incredible event. The final moments, when the two black holes are orbiting each other at a significant fraction of the speed of light just before they collide, will produce gravitational waves so strong that they'll ripple across the universe. Unfortunately, we won't be able to detect those waves directly with current detectors. The gravitational waves from supermassive black hole mergers have frequencies too low for ground-based detectors like LIGO. We'd need space-based detectors like the proposed LISA mission. But we'll probably be able to see the electromagnetic signature. When the black holes merge, they'll disturb the accretion disks around them, potentially triggering a flare of radiation. The final merged black hole will weigh somewhere around 100 million solar masses, the sum of Sagittarius A star and Andromeda's black hole, and it will sit at the center of the new merged galaxy, which astronomers have already nicknamed Milky Way. That's billions of years in the future, though. What about the nearer future? Well, one thing that might happen is that Sagittarius A star could experience a tidal disruption event that we actually get to see. If a star happens to wander too close in the next few decades or centuries, while we have the instruments to observe it, we'll get a front-row seat to one of the most violent events in the universe. The chances of that happening in any given year are small, but over decades, the odds add up, and we're watching more carefully than ever before. We're also going to get better images of Sagittarius A star. The Event Horizon Telescope is adding more telescopes to its network, which will improve resolution and allow us to make movies of the material orbiting the black hole rather than just static images. Imagine watching the superhot gas swirl around the event horizon in real time, seeing flares and instabilities develop, tracking the motion of bright spots as they orbit at close to the speed of light. That's the kind of data we'll have in the next few years. We're also going to continue tracking the stars orbiting the black hole. There are proposals to look for planets orbiting those stars, which would be absolutely wild. A planet orbiting a star that's orbiting a supermassive black hole. The gravitational environment would be incredibly complex. And we're going to look for gravitational wave signatures. While we can't detect the gravitational waves from Sagittarius A star itself with current technology, we might be able to detect waves from black holes or neutron stars in the galactic center region. There's a technique called pulsar timing that uses the regular pulses from pulsars as a kind of galactic-scale gravitational wave detector. Arrays of pulsars across the galaxy can detect the subtle stretching and squeezing of space caused by passing gravitational waves. Now, let's talk about one of the deepest mysteries associated with black holes: the information paradox. According to quantum mechanics, information can't be destroyed. If you know the complete state of a system at one time, you can, in principle, calculate its state at any other time, forward or backward. The laws of physics are deterministic and reversible at the quantum level. But black holes seem to destroy information. If you throw something into a black hole, all the information about what that thing was made of, its quantum state, everything about it, seems to disappear behind the event horizon. For a long time, people thought, well, that information is still there, inside the black hole. It's hidden, but not destroyed. But then, Stephen Hawking showed in the 1970s that black holes aren't completely black, they radiate. This radiation, now called Hawking radiation, comes from quantum effects right at the event horizon. Here's a simplified version of how it works. In quantum mechanics, empty space isn't really empty. There are constant fluctuations where particle-antiparticle pairs pop into existence and annihilate each other almost immediately. Normally, you never notice this because the particles exist for such a short time. But right at the event horizon of a black hole, something interesting can happen. A particle-antiparticle pair can pop into existence with one particle just inside the horizon and one just outside. The one inside falls into the black hole and can't escape. The one outside can escape. From a distance, it looks like the black hole emitted a particle. The energy for that particle has to come from somewhere, and it comes from the black hole's mass. So over time, the black hole loses mass through Hawking radiation, very slowly. For a black hole the size of Sagittarius A star, the rate is absurdly tiny, much slower than the rate it's gaining mass from accretion. But in principle, if you waited long enough and the black hole stopped accreting, it would eventually evaporate completely. Here's the problem. The Hawking radiation is thermal. It's just random heat, like the radiation from a hot piece of metal. There's no information in it about what fell into the black hole. So if a black hole eventually evaporates away completely, where did the information about everything that fell in go? It seems to have been destroyed, violating the principles of quantum mechanics. This is the information paradox, and it's been a major problem in theoretical physics for 50 years. There have been many proposed solutions. Maybe the information is somehow encoded in the Hawking radiation in subtle correlations we haven't figured out how to detect. Maybe it escapes at the very end when the black hole is about to evaporate completely. Maybe it never really goes into the black hole in the first place, but gets smeared over the event horizon in a way that preserves information. A lot of recent work has focused on the idea that black holes might be more complicated than we thought. Maybe the event horizon isn't a simple boundary, but has structure. Maybe there's a quantum fuzziness to it that encodes information about what's fallen in. The truth is, we don't know. Solving the information paradox probably requires a full theory of quantum gravity, something that unites quantum mechanics and general relativity. We don't have that yet. But studying real black holes like Sagittarius A star might give us clues. The more we learn about how black holes behave in practice, the more constraints we have on what theories are possible. Related to the information paradox is an idea called the holographic principle. This is one of the strangest ideas in modern physics, and it came out of thinking about black holes. Here's the basic idea. The information content of a region of space is determined not by the volume of that region, but by the area of its boundary. That sounds bizarre, but there are good reasons to think it's true. The maximum amount of information you can pack into a region of space is determined by how many ways you can arrange matter and energy before it collapses into a black hole. And it turns out that limit is proportional to the surface area of the region, not its volume. For a black hole, all the information about what's inside is somehow encoded on the event horizon, the surface. The event horizon is like a hologram that contains all the information about the three-dimensional interior. If the holographic principle is true, it has profound implications. It suggests that our three-dimensional universe might actually be a projection of information encoded on a two-dimensional surface, like the hologram on a credit card that looks three-dimensional but is really just a two-dimensional pattern. This isn't science fiction. This is serious physics, and some of the smartest people in the world take it seriously. There are even specific mathematical models, like the ADS-CFT correspondence, that show explicitly how a theory of gravity in a certain kind of space is equivalent to a theory without gravity in one fewer dimension. What does this have to do with Sagittarius A star? Well, every black hole is a test case for these ideas. The event horizon of Sagittarius A star, with its surface area of about 1 trillion square kilometers, would encode an enormous but finite amount of information according to the holographic principle. We can't directly test the holographic principle with observations of Sagittarius A star. Not yet, anyway. But understanding black holes is key to developing and testing these fundamental ideas about the nature of reality. Here's something cool. We've actually heard a black hole. Not Sagittarius A star, unfortunately, but black holes in general. In 2015, LIGO detected gravitational waves for the first time, and those waves came from two black holes, each about 30 times the mass of the Sun, spiraling into each other and merging. Gravitational waves are ripples in space-time itself, traveling at the speed of light. They're produced whenever massive objects accelerate, but they're so weak that you need incredibly violent events and incredibly sensitive detectors to see them. LIGO is sensitive enough to detect a change in the distance between its mirrors of less than 1,000th of the width of a proton. That's the level of precision needed to detect gravitational waves passing by Earth. When LIGO detected that first signal, scientists converted the gravitational wave pattern into sound. It made a distinctive chirp, rising in frequency and amplitude before abruptly cutting off as the black holes merged. That chirp is literally the sound of space-time ringing like a bell. We haven't detected gravitational waves from Sagittarius A star itself because it's currently not doing anything violent enough to produce waves we can detect. But if it were to merge with another black hole, or if something very massive were to fall into it in a particular way, we might detect gravitational waves. There are also persistent gravitational waves produced by anything that's not perfectly spherical and spinning. If Sagittarius A star has any bumps or asymmetries and it's spinning, it would produce very faint gravitational waves at a frequency related to its spin rate. Those waves would be far too faint for current detectors, but maybe someday. There's also something called the stochastic gravitational wave background. This is a sort of background hum of gravitational waves from countless sources all over the universe, including from supermassive black hole mergers in distant galaxies. Pulsar timing arrays are starting to detect hints of this background. So, in a sense, we're hearing the whispers of countless black holes across the cosmos, all contributing to this gravitational wave symphony. Here's a weird connection. Black holes might have something to do with why life exists. I know that sounds crazy. Black holes are destructive. They rip things apart. How could they have anything to do with creating life? It's indirect, but the logic goes like this. The heavy elements that make up everything we care about, carbon, oxygen, nitrogen, iron, all the stuff that's not hydrogen or helium, were created inside stars or in supernova explosions. Stars are born from clouds of gas that collapse under their own gravity. Those clouds need to be dense enough and cold enough to collapse, and that means they need to lose energy somehow. One way gas clouds lose energy is by radiating it away. But to radiate efficiently, the gas needs to contain molecules and dust that can emit radiation. And those molecules and dust grains are made of heavy elements. So where did the first heavy elements come from, the ones that allowed later generations of stars to form more efficiently? Some of them came from the first generation of stars, which formed from pure hydrogen and helium left over from the Big Bang. Those stars exploded as supernovae and seeded the universe with heavy elements. But some of those heavy elements might have come from accretion disks around black holes, including the supermassive black holes at the centers of early galaxies. The conditions in an accretion disk are extreme. Temperatures and densities are high enough for nuclear reactions to occur. It's possible that accretion disks around supermassive black holes in the early universe were sites of heavy element production. Those heavy elements would then be distributed into the surrounding gas by winds and jets from the black hole, enriching the gas and making it easier for new stars to form. Those new stars could then form planets, and on some of those planets, life could emerge. Life that's built from carbon and other heavy elements that might have, in part, come from black holes. It's speculative, and the contribution from this process might be small compared to supernovae, but it's a reminder that everything in the universe is connected. The monster at the center of our galaxy might have played a role, however small, in creating the conditions that allowed us to exist. We've learned an enormous amount about Sagittarius A star in the last few decades. We've measured its mass precisely. We've tracked stars whipping around it at absurd speeds. We've imaged its shadow and confirmed that it matches our predictions from general relativity. But there's still so much we don't know. We don't know exactly how fast it's spinning. We don't know its complete feeding history. We don't know if it has a binary companion or if it's ever merged with other black holes. We don't understand all the details of how the accretion disk works, how magnetic fields are generated and evolve, how jets form when they do form. We don't know what happens inside the event horizon. We probably never will, because no information can come back out to tell us. And we're still working on the big theoretical questions. How does quantum mechanics work in the presence of strong gravity? What happens at the singularity? Is the holographic principle correct? How is information preserved? Sagittarius A star is our nearest laboratory for exploring these questions. It's not the biggest or the most active supermassive black hole, but it's the closest, and that makes it incredibly valuable. Every new observation, every new technique brings us a little closer to understanding not just this particular black hole, but black holes in general, and through them, the fundamental nature of space, time, and gravity. Let's talk about how we actually study Sagittarius A star. What tools and techniques make these observations possible? First, there's radio astronomy. Radio waves penetrate the dust and gas between us and the galactic center much better than visible light, so radio telescopes have been essential for studying Sagittarius A star since the beginning. The Very Large Array in New Mexico, the Atacama Large Millimeter Array in Chile, and many other radio observatories around the world regularly observe the galactic center. They map the structure of the gas, detect flares in emission, and contribute to efforts like the Event Horizon Telescope. Then there's infrared astronomy. Infrared light also penetrates dust better than visible light, and it's perfect for studying the stars near Sagittarius A star. Telescopes like the Keck Observatory in Hawaii and the Very Large Telescope in Chile use adaptive optics to compensate for atmospheric blurring and can track individual stars with incredible precision. These observations over many years have given us the orbital data that proved the black hole's existence and measured its mass. X-ray telescopes are important too. The Chandra X-ray Observatory has observed Sagittarius A star many times, catching flares when the black hole's activity increases briefly and studying the hot gas in the region. And then there's the Event Horizon Telescope, which we've talked about. This global array of radio telescopes working together represents the cutting edge of what's possible with current technology. But we're not stopping here. New instruments are always being developed. There are proposals for space-based interferometers that could achieve even higher resolution than the Event Horizon Telescope. There are plans for more sensitive gravitational wave detectors that could catch signals from black holes like Sagittarius A star. There's even been talk about sending a probe to the galactic center. It would take thousands of years with current technology, but in principle, we could get a much closer look. Every advance in technology opens new windows on the universe. Who knows what we'll discover about Sagittarius A star in the coming decades? Let's step back and think about what Sagittarius A star means in the broader context of the universe. Supermassive black holes aren't rare. We think most large galaxies have them. Observational campaigns have found supermassive black holes in thousands of galaxies, and indirect evidence suggests they're a common feature. That means there are at least as many supermassive black holes in the universe as there are galaxies, probably hundreds of billions of them in the observable universe alone. Each one is a similar kind of object to Sagittarius A star, following the same laws of physics, warping space-time in the same way, feeding on gas and stars, potentially producing jets and affecting its host galaxy. But each one also has its own history, its own quirks, its own relationship with its environment. Some are much bigger than Sagittarius A star, some are smaller. Some are actively feeding and blazingly bright. Some are quiet like Sagittarius A star is now. Studying the population of supermassive black holes across the universe tells us about how galaxies evolve over cosmic time. We can see how the typical mass of a central black hole changes as the universe ages. We can see how often black holes merge. We can see how black hole activity relates to star formation in galaxies. This is the field of extragalactic astronomy, and it's revealed that the universe is far more dynamic and interconnected than we once thought. Galaxies aren't just collections of stars floating in space. They're complex systems where stars, gas, dark matter, and black holes all influence each other. And at the center of it all, in most cases, sits a supermassive black hole, the dark heart of the galaxy. Sagittarius A star is our local example. It's special to us because it's our black hole, the one at the center of our galaxy. But it's also a representative of this ubiquitous class of objects that play a crucial role in the cosmos. There's something profound about knowing that there's a black hole at the center of our galaxy. It's not just an abstract scientific fact. It's part of our cosmic address. We live on Earth, which orbits the Sun, which is one star among hundreds of billions in the Milky Way, which is organized around and held together in part by a supermassive black hole called Sagittarius A star. That black hole has been there for billions of years, long before our Sun formed, long before Earth existed, long before life emerged. It will be there long after we're gone, long after the Sun dies, long after every star currently in the sky has burned out. It's humbling. We're so small compared to something like Sagittarius A star. Our entire planet could fall into it and not even be noticed. It would barely add to the black hole's mass. But at the same time, we, tiny humans, have figured out it's there. We've measured it. We've photographed it. We understand, at least in part, what it is and how it works. That's the power of science and human curiosity. We might be small, but our minds can reach out across 26,000 light-years and comprehend something as extreme and strange as a supermassive black hole. There's something beautiful about that. We're part of a universe that includes black holes and galaxies and cosmic expansion, and we're capable of understanding our place in it. Let's address some common misconceptions about black holes, including Sagittarius A star. Misconception number 1. Black holes suck everything in like a vacuum cleaner. We've already talked about this, but it bears repeating. Black holes have gravity, just like any massive object. If you're far enough away, their gravity is no different than any other object with the same mass. They're only dangerous if you get very close. Misconception number 2. Black holes are cosmic portals or wormholes. In general relativity, certain solutions to Einstein's equations do describe wormholes, tunnels through space-time that could theoretically connect distant parts of the universe or even different universes. But there's no evidence that real black holes are wormholes. The simplest black hole solutions don't include wormholes, and even the solutions that do would require exotic forms of matter we've never seen to keep them stable. Misconception number 3. If you fell into a black hole, you could travel back in time or to another universe. The time dilation near a black hole is real, but it doesn't let you travel backward in time. From your perspective falling in, you'd just fall toward the center. From an outside perspective, you'd appear to slow down and never quite reach the event horizon. But there's no time travel involved, not in the sense of going backward. Misconception number 4. Black holes live forever. Actually, Hawking radiation means that black holes can evaporate. It takes an absurdly long time for a supermassive black hole like Sagittarius A star to evaporate, much longer than the current age of the universe, but in principle, they don't last forever. Misconception number 5. We know what's inside a black hole, we don't. General relativity predicts a singularity, a point of infinite density at the center, but general relativity breaks down under those conditions. We need a theory of quantum gravity to really understand what happens there, and we don't have one yet. It's possible that the singularity is replaced by something else, some kind of quantum structure. We just don't know. Misconception number 6. Black holes are empty space. They're not. They contain mass, a lot of it. It's just compressed into a very small volume. The event horizon is a boundary, not a physical surface, but the mass is real and it's there. Understanding what black holes really are, as opposed to the myths and science fiction versions, makes them even more fascinating. Reality is stranger and more interesting than fiction. We're living in a golden age of black hole research. We've confirmed that supermassive black holes exist. We've imaged them. We've detected gravitational waves from merging black holes. We've tracked stars orbiting them at relativistic speeds. But every answer raises new questions. How did the first supermassive black holes form? What happens to information that falls into a black hole? How do jets work exactly? What's the structure of space-time at the event horizon and beyond? Sagittarius A star will continue to be a focus of research for decades to come. As our instruments improve, we'll learn more and more about this dark heart of the Milky Way. We'll track more stars in even tighter orbits. We'll make movies showing the dynamics of the accretion disk in real time. We'll measure the black hole's spin precisely. We'll look for gravitational wave signals. We'll study how the black hole interacts with its environment. And through all of this, we'll gain insight not just into one particular black hole, but into the fundamental laws that govern the universe. Because that's what black holes are. They're natural laboratories for studying gravity, space-time, and quantum mechanics under the most extreme conditions nature allows. They push our theories to their limits and show us where our understanding breaks down. Every time we learn something new about Sagittarius A star, we learn something new about physics itself. Imagine for a moment that you could take a journey to the galactic center, to the black hole itself. You'd start here, in our solar system, 26,000 light-years from the target. Even traveling at the speed of light, it would take 26,000 years to get there. But let's pretend we have faster than light travel, just for this thought experiment. As you traveled toward the galactic center, you'd notice the density of stars increasing. In our neighborhood, the nearest star to the Sun is over 4 light-years away. Closer to the galactic center, stars are separated by only fractions of a light-year. The sky would get brighter. More and more stars would be visible, until eventually the combined light of millions of stars would be bright enough to read by, even at night. You'd see massive young stars, blazingly bright, living fast and dying young. You'd see ancient red giants, stars at the end of their lives. You'd see pulsars, rapidly spinning neutron stars left over from supernova explosions. As you got within a few light-years of the center, you'd start to see the effects of the black hole's gravity on the stellar orbits. Stars would be moving at strange angles, some in highly elliptical orbits, some in nearly circular ones, but all organized around an invisible center. You'd detect high-energy radiation, X-rays and gamma rays from the superhot gas swirling around the black hole. You'd see the radio emissions from the accretion disk. And then, if you got close enough and looked at the right wavelengths, you'd see it, the shadow, the dark circle against the glowing background, marking the presence of the event horizon. You'd see the light from the accretion disk bent into strange patterns by the extreme gravity. Light that should be behind the black hole would be bent around it, creating a bright ring. Light from the side of the disk moving toward you would be blue-shifted and brightened. Light from the side, moving away, would be red-shifted and dimmed. If you were foolish enough to get too close, you'd start to feel the tidal forces. Your body would be stretched in the direction of the black hole and compressed perpendicular to it. This effect, called spaghettification, would eventually tear you apart if you crossed the event horizon of a small black hole. For our galactic center, though, because it's so massive, the tidal forces at the event horizon aren't immediately lethal. You could cross the event horizon and survive, at least for a moment. But once you crossed, there'd be no coming back. All paths would lead inward. You'd fall toward the singularity, and eventually, the tidal forces would grow strong enough to rip you apart at the atomic level. The journey would end at the singularity itself, that point where our understanding of physics breaks down and we don't know what happens. Of course, this is all hypothetical. We can't actually make this journey, but we can observe from a distance, and what we see is amazing enough. One of the most mind-bending things about the galactic center is how it warps space and time itself. This isn't science fiction, it's real physics, predicted by Einstein and confirmed by observation. We've already discussed time dilation and how time runs slower near massive objects. But there are other effects of space-time curvature that are equally fascinating. One is gravitational lensing. Light traveling near a massive object gets bent by the curvature of space-time. We see this effect throughout the universe. Distant galaxies get distorted and magnified by foreground galaxy clusters. The effect is so strong that we sometimes see multiple images of the same galaxy, bent around the cluster like light through a lens. Near the black hole, gravitational lensing becomes extreme. Light from the accretion disk doesn't travel in straight lines. It follows curved paths through the warped space-time. This is actually why we see a bright ring in the Event Horizon Telescope image. Light from the backside of the accretion disk gets bent around the black hole, allowing us to see it even though it's behind the black hole from our perspective. There's also an effect called Doppler beaming. When material in the accretion disk moves toward us at close to the speed of light, its light gets blue-shifted and brightened. When it moves away from us, the light gets red-shifted and dimmed. This creates an asymmetry in the brightness of the ring we observe. The combination of gravitational lensing, Doppler beaming, and the black hole's spin creates a complex pattern in the light we detect. By carefully analyzing this pattern, astronomers can tease out information about the black hole's properties. Another fascinating effect is the precession of orbits. In Newtonian gravity, a planet orbiting the Sun would trace out a perfect ellipse that repeats exactly each orbit. But in general relativity, the intense gravity near a black hole causes the ellipse itself to slowly rotate. This orbital precession has been measured for S2 and matches Einstein's predictions perfectly. Over many orbits, the path the star traces out looks like a rosette pattern, with the ellipse slowly rotating around the black hole. But perhaps the strangest effect is what happens to space itself very close to the event horizon. There's a region called the photon sphere, located at 1.5 times the event horizon radius. At this distance, light can orbit the black hole. Imagine a photon traveling tangent to the photon sphere. Instead of continuing in a straight line, it curves around the black hole and comes back to where it started, trapped in a circular orbit. Of course, this orbit is unstable. Any slight perturbation will cause the photon to either spiral inward into the black hole or escape outward. But in principle, you could have light orbiting the black hole indefinitely at this special radius. This means if you could somehow position yourself at the photon sphere and look in any direction, you'd see the back of your own head. Light from you would orbit the black hole and return to your eyes. It's one of the strangest predictions of general relativity. The Fermi bubbles are among the most dramatic pieces of evidence for the black hole's violent past. But what do they actually tell us about what happened? First, let's talk about the sheer scale. Each bubble is roughly 25,000 light-years across. To put that in perspective, that's almost as far as we are from the galactic center. These structures extend from deep in the southern hemisphere of the galaxy to deep in the northern hemisphere, towering above and below the galactic plane. They emit primarily in gamma rays, the highest energy form of light. This tells us they're filled with extremely energetic particles, electrons and positrons moving at close to the speed of light. But here's what's really interesting. The edges of the bubbles are remarkably sharp. They're not fuzzy or diffuse. There's a clear boundary between the inside of the bubble and the surrounding gas. This sharpness tells us something about how they formed. If the bubbles had inflated slowly over millions of years, we'd expect fuzzy edges as the material gradually mixed with its surroundings. But sharp edges suggest a more explosive origin. The leading theory is that they were blown out by a powerful wind or jet from the black hole during a period of intense feeding activity. The energy required to create these structures is staggering. Estimates suggest it would have taken about 10 to the 54 ergs, roughly equivalent to 100,000 supernovae going off simultaneously, or the energy released by 100,000 solar masses being converted directly into energy via E equals mc squared. That's an enormous amount of energy. Where did it come from? The Fermi bubbles are among the most dramatic pieces of evidence for the black hole's violent past. But what do they actually tell us about what happened? First, let's talk about the sheer scale. Each bubble is roughly 25,000 light-years across. To put that in perspective, that's almost as far as we are from the galactic center. These structures extend from deep in the southern hemisphere of the galaxy to deep in the northern hemisphere, towering above and below the galactic plane. They emit primarily in gamma rays, the highest energy form of light. This tells us they're filled with extremely energetic particles, electrons and positrons moving at close to the speed of light. But here's what's really interesting. The edges of the bubbles are remarkably sharp. They're not fuzzy or diffuse. There's a clear boundary between the inside of the bubble and the surrounding gas. This sharpness tells us something about how they formed. If the bubbles had inflated slowly over millions of years, we'd expect fuzzy edges as the material gradually mixed with its surroundings. But sharp edges suggest a more explosive origin. The leading theory is that they were blown out by a powerful wind or jet from the black hole during a period of intense feeding activity. The energy required to create these structures is staggering. Estimates suggest it would have taken about 10 to the 54 ergs, roughly equivalent to 100,000 supernovae going off simultaneously, or the energy released by 100,000 solar masses being converted directly into energy via E equals mc squared. That's an enormous amount of energy. Where did it come from? The most likely source is accretion onto the black hole. If a massive gas cloud, perhaps containing 1 million solar masses or more, fell into the central region and fed the black hole over a period of a few million years, it could release enough energy to inflate these bubbles. There's also evidence from X-ray observations of structures that might be related to the Fermi bubbles. What astronomers call X-ray chimneys seem to connect the galactic center to the base of the bubbles. These could be the channels through which hot gas and energy flowed outward during the active phase. And there are other structures in the galactic center that might be related. There's a radio structure called the radio arc, vertical filaments of synchrotron emission that might trace out magnetic field lines connected to past outbursts. The timing is interesting too. The bubbles are estimated to be 6 to 10 million years old. That's recent in cosmic terms. It means the galaxy looked very different just a few million years ago. If there were intelligent observers in the galaxy back then, they would have seen the galactic center blazing brilliantly, possibly outshining all the stars in the central region. This raises a question. How often does this happen? Is it a rare event, occurring once every 100 million years, or is it more common, perhaps happening every 10 million years or so? We don't know yet, but studying the Fermi bubbles and similar structures in other galaxies might give us clues. Astronomers are constantly monitoring the galactic center, watching for the next big event, and there are several candidates for what might happen next. The G objects we mentioned earlier are still being tracked. While G2 survived its 2014 close passage, it's still in a tight orbit and will make another approach. The other G objects, G1 through G6, are also on trajectories that bring them close to the black hole periodically. Each time one of these objects makes a close pass, there's a chance something dramatic could happen. If the dust shell around one of them is thicker than we think, or if the central star is smaller or weaker, the tidal forces might finally win and tear the object apart. Beyond the G objects, there are monitoring programs tracking hundreds of stars in the galactic center region. Some of these stars are in orbits that will bring them progressively closer over the coming decades. Others might have close encounters with each other that perturb their orbits dramatically. There's also the possibility of a gas cloud wandering in from farther out. The galactic center isn't a static environment. Gas is constantly flowing through the region, blown by stellar winds, compressed by supernova shock waves, and pulled by the black hole's gravity. Every now and then, a dense clump might find its way to the inner region. If it's massive enough and comes in at the right angle, it could provide a substantial meal for the black hole, triggering an outburst that would make the galactic center dramatically brighter for months or even years. The waiting game is part of what makes studying the galactic center so interesting. We know dramatic events happen, the Fermi bubbles prove that, but we don't know when the next one will occur. It could be tomorrow. It could be 1,000 years from now. But when it happens, we'll be watching. Modern telescopes are constantly monitoring the galactic center in multiple wavelengths. If there's a brightening, if there's a change, instruments around the world will detect it within hours. The region around the black hole is one of the strangest environments in the galaxy. It's incredibly crowded, with stars packed so closely together that interactions between them are common. In our neighborhood of the galaxy, stars are separated by light years. The nearest star to the Sun is over 4 light years away. Close encounters between stars are extremely rare. But in the central light year of the galaxy, there are millions of stars. The density is about 1 million times higher than in our solar neighborhood. Stars pass within light days or even light hours of each other regularly. This creates a very dynamic environment. Gravitational interactions between stars are frequent. Some stars get flung outward at high speeds, becoming what astronomers call hypervelocity stars. These are stars moving so fast that they're escaping the galaxy entirely. Other stars have their orbits dramatically altered. A star in a relatively safe orbit might have a close encounter with another star and get perturbed into an orbit that brings it much closer to the black hole. The galactic center is also home to some of the most massive stars known. There's a cluster of very young, very massive stars within a few light years of the black hole. Some weigh more than 100 times the mass of the Sun. These stars are puzzling because they shouldn't be there. The tidal forces near the black hole should prevent star formation in this region. So how did these massive stars get there? One theory is that they formed farther out and then migrated inward through gravitational interactions. Another suggests they formed in a massive disk of gas that temporarily existed around the black hole millions of years ago. What's clear is that the galactic center is a laboratory for studying stellar physics in extreme conditions we can't replicate anywhere else. The black hole at the center of our galaxy isn't just sitting there doing nothing. It plays an active role in how the galaxy evolves over billions of years. When the black hole feeds actively, it releases enormous amounts of energy. This energy heats the surrounding gas and blows it away, preventing it from falling into the black hole and preventing it from forming new stars. This is called negative feedback. But there can also be positive feedback. The energy released can compress gas in certain regions, triggering bursts of star formation. The shock waves from black hole outbursts can travel through the galaxy, creating dense regions where new stars can form. There's also a relationship between the mass of a galaxy's central black hole and the properties of the galaxy itself. More massive galaxies tend to have more massive central black holes. This relationship suggests that galaxies and their central black holes must grow together, influencing each other through feedback mechanisms. In the early universe, supermassive black holes may have formed first and actually seeded the regions where galaxies would grow. Or galaxies formed first and black holes grew within them. The truth is probably somewhere in between, with black holes and galaxies co-evolving from the earliest moments. Understanding the black hole at the center of our galaxy helps us understand galaxy formation and evolution throughout the universe. One of the biggest unsolved questions is how the black hole at the galactic center formed in the first place. We know how stellar mass black holes form. A massive star runs out of fuel, its core collapses, and if enough mass collapses, it forms a black hole. But supermassive black holes are millions or billions of times more massive. You can't make one just from a single star. The obvious answer is that they grew over time. Maybe a stellar mass black hole formed first, then gradually consumed gas, dust, and stars over billions of years. But there's a problem. We found supermassive black holes in the very early universe, less than 1 billion years after the Big Bang. That's not enough time for a stellar mass black hole to grow into a billion solar mass monster. So there must be ways to create large black holes more quickly. Maybe in the early universe, massive gas clouds collapsed directly into black holes weighing thousands or millions of solar masses. Maybe there were very massive stars that existed only in the early universe that collapsed directly into massive black holes. For our galactic center specifically, it probably grew primarily by accreting gas over billions of years, with occasional contributions from stars that got too close and from mergers with smaller black holes when satellite galaxies fell into the Milky Way. In about 4.5 billion years, something dramatic will happen to the Milky Way. We're going to collide with Andromeda. The two galaxies are approaching at about 110 kilometers per second. When they meet, it won't be a simple crash. Galaxies are mostly empty space. Individual stars will pass by each other without colliding. But the gravitational dance will be spectacular. Computer simulations show the galaxies will pass through each other multiple times, their shapes distorting with each passage. Gas clouds will collide and compress, triggering massive bursts of star formation. The night sky for any observers present would transform dramatically with each close approach. Both galaxies have supermassive black holes at their centers. Andromeda's is much more massive than ours, perhaps 100 to 200 million solar masses. When the galaxies merge, these black holes will eventually find each other. Here's where it gets interesting. Two supermassive black holes don't just immediately merge. First, they sink toward the center of the combined galaxy through a process called dynamical friction. As each black hole moves through the sea of stars, gravitational interactions with those stars slow it down, causing it to lose orbital energy and spiral inward. This process takes millions of years. During this time, the two black holes are orbiting each other at large distances, perhaps light years apart. As they get closer, they start to interact more directly. They'll reach a point where they're orbiting each other every few years, then every few months, then every few days. Stars unfortunate enough to pass between them can get flung away at incredible speeds, ejected from the galaxy entirely. Eventually, the black holes get close enough that gravitational wave emission becomes significant. At this point, they start radiating energy in the form of gravitational waves, which causes their orbit to decay rapidly. The final moments are extraordinary. The black holes spiral inward at an ever-increasing rate, moving faster and faster, radiating more and more gravitational waves. In the last few orbits before merger, they're moving at significant fractions of the speed of light, orbiting each other hundreds of times per second. Then they merge. The two event horizons touch and merge into a single, larger event horizon. The combined black hole has a mass equal to the sum of the two original black holes, minus a few percent that was radiated away as gravitational waves during the merger. But here's the really strange part. The merger doesn't happen symmetrically. If the two black holes had different spins, or if they merged at an angle, the final black hole can receive a kick, a recoil velocity from the asymmetric emission of gravitational waves. This kick can be strong enough to eject the merged black hole from the center of the galaxy entirely. It would wander through the galaxy for millions of years before settling back to the center. The final merged black hole will weigh roughly 100 million solar masses, and it will sit at the heart of what astronomers call Milky Way, an elliptical galaxy that will be all that's left of the Milky Way and Andromeda. The study of the galactic center is driving remarkable technological advances, and the next decade promises even more breakthroughs. The Event Horizon Telescope continues to expand. New telescopes are being added to the network, including facilities in Greenland, France, and Arizona that became operational in 2023 and 2024. Each new telescope increases the effective resolution and allows for better image reconstruction. But more importantly, the network is now capable of observing at multiple frequencies simultaneously. The original Sagittarius A image was made at 1.3 millimeters wavelength. Now they're adding observations at shorter wavelengths, which penetrate closer to the event horizon and reveal finer details. By 2026, the collaboration hopes to produce the first movies of material orbiting the black hole. Instead of a single static image, we'll see how bright spots in the accretion disk move and evolve over hours. This will directly show us the dynamics of material spiraling inward. There are also proposals for space-based very long baseline interferometry. Imagine Event Horizon Telescope, but with one or more telescopes in orbit. This would dramatically increase the baseline and allow for even higher resolution imaging. Such a mission could potentially resolve details smaller than the event horizon itself. On the X-ray front, several missions are planned or proposed. The European Space Agency's Athena mission, scheduled for the early 2030s, will have sensitivity far exceeding current X-ray telescopes. It will be able to detect much fainter flares and study the hot gas around the black hole in unprecedented detail. NASA has also funded studies for missions specifically designed to study black hole environments. One concept involves an X-ray polarimetry mission that would measure not just the intensity of X-rays, but their polarization, revealing the geometry of magnetic fields near the event horizon. For gravitational wave detection, the LISA mission remains the best hope for detecting waves from supermassive black hole mergers. While it won't detect waves from our black hole in its current quiet state, it could detect a merger if our black hole were to consume an intermediate mass black hole. LISA is scheduled for launch in the mid-2030s. There are also ground-based initiatives. The Next Generation Event Horizon Telescope, sometimes called NGEHT, is being designed to have 10 times the sensitivity and angular resolution of the current array. This would allow it to image fainter sources and resolve structures that are currently invisible. And then there's artificial intelligence. Machine learning algorithms are being developed to analyze the enormous datasets from these telescopes. Traditional analysis methods struggle with the sheer volume of data and the complexity of the signals. AI can identify patterns and extract information that would be impossible for humans to find manually. One particularly exciting application is using AI to predict when the black hole might flare. By analyzing years of monitoring data, algorithms might be able to identify subtle precursors that indicate a brightening event is about to occur. This would allow telescopes around the world to coordinate observations and catch the flare in real time. The existence of the supermassive black hole at the center of our galaxy raises profound questions about our place in the universe. We used to think Earth was at the center of everything. Then we learned we orbit the Sun. Then we learned the Sun is just one star among billions, not even at the center of the galaxy, but out in the suburbs. Now we know that at the center is a black hole, a region where normal physics breaks down, where time and space become so warped that our intuitions completely fail. We're not at the center of anything. We're in a quiet corner, far from the violent heart, and that's probably good. Being at the center would be dangerous. There's something humbling about knowing the galaxy is organized around this massive object we can barely observe, that operates according to rules alien to our everyday experience. There's also the question of information. According to quantum mechanics, information can't be destroyed, but black holes seem to destroy information. Anything that falls in appears to be erased from the universe. Stephen Hawking showed that black holes emit radiation through quantum effects, causing them to slowly evaporate. But the radiation seems random, with no information about what fell in. So when a black hole evaporates completely, where did the information go? This is the black hole information paradox. Various solutions have been proposed, but the true answer probably requires a theory of quantum gravity that unites quantum mechanics and general relativity. The black hole at our galactic center is one of the best places to look for clues about what that unified theory might look like. Behind all the science, there's a human story. The story of people who dedicated their lives to understanding the galactic center. Andrea Ghez and Reinhard Genzel spent decades tracking stars orbiting the black hole, eventually proving it existed and winning the Nobel Prize. Teams of scientists and engineers built the Event Horizon Telescope, coordinating observations across the planet to capture the first image. There are telescope operators who work night shifts, grad students who analyze data, theorists who develop models, programmers who write software. Hundreds of people working together over decades, slowly piecing together the puzzle. Science isn't done by lone geniuses. It's done by communities collaborating, building on each other's work, sometimes disagreeing, but always pushing forward. We're living through a golden age of black hole research. Things that were pure theory 50 years ago are now being observed directly. Questions that seemed unanswerable are being answered. Every answer raises new questions. Every observation reveals new mysteries. The black hole at the center of our galaxy is a window into the most extreme physics in the universe, a laboratory for testing our theories, a clue to how galaxies form. It's been there for billions of years. It will be there for billions more. Long after our sun dies, the black hole will still be there, patiently waiting, occasionally flaring when something falls too close. It's the dark heart of the Milky Way, the secret at the center, the anchor around which everything revolves. So what are the biggest secrets of the Milky Way's dark heart? What have we learned, and what remains mysterious? We've learned that there's a supermassive black hole with 4 million times the mass of the Sun sitting at the center of our galaxy. We've learned that it's relatively quiet right now, but was probably more active in the past. We've learned that the extreme conditions near it let us test general relativity in ways we can't do anywhere else, and so far, Einstein's theory passes every test. We've learned that black holes aren't just oddities. They're fundamental components of galaxies, shaping galactic evolution through their feedback on star formation and their role in organizing the central regions of galaxies. But mysteries remain. How did supermassive black holes form in the first place? How fast is our galactic center spinning? And what does that tell us about its history? What happens inside the event horizon? How is information preserved when something falls into a black hole? These questions touch on the deepest problems in physics. They require us to understand how quantum mechanics and gravity work together, something we don't fully understand yet. The black hole at the center of our galaxy is more than just an astronomical object. It's a window into the fundamental nature of reality. Every observation we make, every detail we uncover, brings us a little closer to answering questions humans have been asking for thousands of years. What is the universe made of? How does it work? What are the limits of knowledge? The dark heart of the Milky Way holds secrets about space, time, gravity, and the ultimate fate of matter. We've come so far in understanding it, but there's still so far to go. We've mapped the orbits of stars around it with incredible precision. We've detected the bending of light and the slowing of time near it. We've imaged its shadow and confirmed it matches our theories. But we still can't see inside. We still don't know exactly what happens at the singularity. We still don't understand how it formed or how it will evolve over the next billions of years. And that's okay. That's what makes science exciting. There's always more to discover, always deeper questions to ask, always new mysteries waiting. The galactic center has taught us humility. It's shown us that the universe is stranger than we imagined, that our theories, as good as they are, still have limits, that there are phenomena so extreme that they push our understanding to the breaking point. But it's also taught us that we can understand things that seem impossible. 20 years ago, people thought we'd never be able to image a black hole. The resolution required seemed impossible to achieve. But we did it. We found a way. 50 years ago, people thought we'd never detect gravitational waves. The signals seemed too weak, the noise too strong. But we did it. We built detectors sensitive enough to measure distortions smaller than a proton. 100 years ago, people didn't even know black holes could exist. They were just strange solutions to Einstein's equations that most people assumed were mathematical curiosities, not real objects. Now we've imaged them. We've detected their gravitational waves. We've measured their effects on surrounding stars and gas. We've proven they're not only real but common, sitting at the centers of most large galaxies. That's the power of science. That's what happens when you combine human curiosity with clever technology and careful observation. Things that seem impossible become possible. Questions that seem unanswerable get answered. And the black hole at the center of our galaxy, that 4 million solar mass monster hiding behind dust and gas 26,000 light-years away, has been one of the greatest challenges and one of the greatest triumphs of modern astronomy. In the short term, we're going to get better observations. The Event Horizon Telescope is continuously improving, adding more telescopes and increasing sensitivity. Within the next few years, we should have movies of the gas orbiting the black hole, showing how it changes over hours to days. We'll be able to watch bright spots in the accretion disk complete orbits in just minutes. These observations will help us understand how gas actually falls into a black hole, what role magnetic fields play, and how flares develop. We'll also get better measurements of the black hole's spin, which tells us about its history. New X-ray telescopes will study the region in more detail, detecting fainter emissions and catching smaller flares. We'll continue tracking the stars orbiting the black hole. By monitoring multiple stars, we can build up a more complete picture of the gravitational field and test general relativity in different ways. Future space-based gravitational wave detectors might detect waves from the galactic center, giving us a completely new way to study it. In the longer term, some scientists have even proposed sending a probe to the galactic center. It would take thousands of years with current technology, but it's not impossible. Such a probe could make measurements impossible from Earth, studying the environment up close. Things that seem impossible have a way of becoming possible given enough time and ingenuity. The last few years have brought surprising discoveries that have changed how we understand the galactic center. One of the most unexpected findings came from analyzing decades of stellar motion data. By studying how the orbits of S-stars have evolved over time, astronomers discovered subtle anomalies that can't be explained by the black hole's gravity alone. Some of these anomalies might be caused by an extended mass distribution around the black hole, perhaps a dense cluster of stellar remnants, or even intermediate mass black holes too faint to detect directly. Other anomalies might hint at dark matter concentrations or even modifications to general relativity at small scales. Another breakthrough involves understanding the magnetic field structure. The polarization observations from the Event Horizon Telescope revealed that magnetic fields near the black hole are surprisingly organized and strong. They're not chaotic tangles, but show clear, large-scale structure. This has implications for how energy is extracted from the black hole and how jets might form. Strong, organized magnetic fields can tap into the black hole's rotational energy through processes we're only beginning to understand. There have also been discoveries about the stellar population near the galactic center. New infrared surveys have identified populations of stars we didn't know existed, including very old stars mixed with the young massive stars we already knew about. This is puzzling because old stars shouldn't be there. They should have been flung away by gravitational interactions long ago. Their presence suggests the galactic center's history is more complex than we thought. Perhaps there were multiple episodes of star formation. Perhaps the central region was more stable in the past than it is now. Or perhaps these old stars were captured from globular clusters that wandered too close and were tidally disrupted. We're also learning about the distribution of dark matter near the galactic center. Theory predicts that dark matter should be concentrated into a dense spike near supermassive black holes. If this spike exists, it might be detectable through its gravitational effects on orbiting stars or through annihilation signals if dark matter particles can destroy each other. Several groups are searching for these signatures, and while nothing definitive has been found yet, the constraints are tightening. Within the next decade, we might either detect this dark matter spike or rule out certain dark matter models. Another area of active research involves the interaction between the black hole and its surrounding environment on larger scales. How does activity at the galactic center affect star formation hundreds or thousands of light years away? How do winds and jets from the black hole interact with the galactic magnetic field? These questions connect the black hole to the larger story of galactic evolution. The answers will help us understand not just our own galaxy, but galaxies throughout the universe. The black hole at the center of our galaxy isn't just important for understanding the Milky Way. It's important for understanding the universe as a whole. Supermassive black holes are common. Most large galaxies have them. That means there are hundreds of billions in the observable universe. Each one is a laboratory for extreme physics, testing the same laws of nature. By studying our galactic center, we're learning about how galaxies form and evolve, how black holes grow, how they interact with their environment, and how they influence star formation. Black holes, despite being tiny compared to galaxies, play an outsized role in cosmic evolution. They regulate galaxy growth, enrich gas with heavy elements, and create powerful winds that can affect entire galaxy clusters. There's also the connection to fundamental physics. Black holes are where quantum mechanics and general relativity come together, where both theories are important and neither can be ignored. Currently, these theories don't work well together. They're based on different principles and make different predictions about extreme conditions. Resolving this, creating a theory of quantum gravity, is one of the great challenges of our time. The black hole at our galactic center is one of the best places to look for clues. Every observation helps constrain the possibilities and guide theorists toward the right answer. We're living in an exciting time for astronomy. Technologies that seemed impossible a generation ago are now routine. The black hole at the center of our galaxy, once just theoretical, is now a confirmed reality we've imaged and studied. But the story isn't over. Every answer raises new questions. What is the black hole doing right now? What will it do in the future? How has it shaped our galaxy over billions of years? These questions will keep astronomers busy for decades. There's something profound about knowing this monster exists at our galaxy's heart. Something humbling about realizing that everything we see is part of a system organized around this invisible center. We orbit not just the Sun, but ultimately the galactic center. The Sun takes 225 million years to complete one orbit. Since dinosaurs walked the Earth, we've completed less than 1/3 of one orbit. The galaxy moves on timescales that dwarf human history. Empires rise and fall, species evolve and go extinct, continents drift, and the galaxy barely notices. It just keeps rotating, carrying us along. For all our knowledge, the galaxy remains mysterious. We don't know what dark matter is. We don't know if we're alone. We don't fully understand how galaxies form. We don't know what the far future holds. These unknowns aren't failures. They're invitations to future generations to keep looking, keep questioning, keep exploring. The dark heart of the Milky Way has revealed many secrets, but it's keeping some still, waiting for the next breakthrough. We started this journey talking about the invisible monster at the heart of our galaxy. The supermassive black hole that weighs 4 million times what our Sun weighs, packed into a region smaller than Mercury's orbit. We've explored how we discovered it, measured it, and finally imaged it. We've talked about stars orbiting it at relativistic speeds, the tidal forces that can tear things apart, and the way it warps space and time itself. We've discussed its violent past and quiet present, the Fermi bubbles that hint at ancient outbursts, the gas clouds that might feed it in the future, the dense stellar environment where millions of stars are packed tight and interactions are common. We've looked at the role it plays in galactic evolution, how it might have helped shape the galaxy over billions of years. We've discussed the mystery of how it formed and looked forward to the future collision with Andromeda. We've connected it to deep questions in physics, to the information paradox, to the search for quantum gravity. And we've celebrated the human achievement of understanding all this, the decades of work by thousands of people building the technology and theories needed to study something so extreme and so far away. The black hole at the center of the Milky Way is no longer unknown. We know it exists, we know its mass, its location, what it's doing, but it remains mysterious in a deeper sense. It's a portal to physics we don't fully understand, a laboratory for testing theories at their limits. It's the dark heart of the Milky Way, the secret at the center, the anchor around which everything revolves. And it's ours to study, to understand, to learn from. A 4 million solar mass teacher, silent and patient, waiting for us to ask the right questions. The journey continues, the mysteries deepen, the discoveries keep coming. Somewhere out there, 26,000 light-years away, hidden behind dust and gas, warping space and time around it, the black hole waits. It's been there for billions of years. It will be there for billions more. And for as long as we're curious, for as long as we ask questions about the universe, we'll keep studying it, keep learning from it, keep pushing to understand the secrets it holds. That's the story of the dark heart of the Milky Way. Not a story with an ending, but one that continues, that evolves, that deepens with every observation and every new idea. It's a story of human curiosity meeting cosmic mystery, of technology and theory revealing what seemed impossible to know. It's a story of a black hole and a species that dares to study it, and it's far from over.